welcome to my channel. Let's have a look at a new problem. Problem 2326, spiral matrix 4 together. So for this problem, we're going to share a solution using the rotation matrix. So first I'll read through the statement of the problem, then analyze the method and explain the idea. And then we share the code and then explain in more detail about the rotation matrix. First, let's look at the statement of the problem. We are given two integers m and n, which represent the dimensions of a matrix. So we are also given a height of a linked list of integers. So we want to generate an m times n matrix that contains the integers in the linked list presented in the spiral order, clockwise, so starting from the top left of the matrix. If there are remaining empty spaces, fill them with -1. So that's the statement of the problem. So we are required to return the matrix in the end. So let's look at example 1. So in example 1, here is a height. This is the element in the linked list. So we start from the top left, 3, and then we continue move to the right horizontally. Then as we arrive at 8. We're going to change direction by 90 degrees. So they walk downwards towards 7. Then when we add 7, we're going to move horizontally to the left up to 5. Then as we are here, so we are going to move upwards vertically to 5, and then from 5 we change direction to horizontal traversal and continue the procedure. And the remaining -2s are places that are not filled with element in height, because the linked list is exhausted. This is example 1. So in example 2, so we have only one row, and then we have 3 elements in the linked list, and then we traverse horizontally, then get 0, 1, 2 set, and then remain -1 in the fourth position. So that's about the examples in the problem statement. Let's look at the constraints about the problem. So the size of matrix is controlled by mn, and m and n can be as large as 10 to the power 5. So it's a large number, right? So together they can have 10 to the power 10 elements in total. So the number of nodes in the list is in the range 1 up to m times n. In other words, so the elements or nodes in the linked list is less or equal than the number of available spots in the matrix. So the node value is controlled by 1000. So that's not very essential for this problem. So here let's comment on the third constraint. So actually, even if the linked list contains more than m by n, m times n elements, we can still do the same procedure. So we just need to initialize a counter. Once the counter exceeds m times n, we just stop, right? So that's the statement about the problem. So let's look at the method here we are going to use. Here the problem is nothing but a spiral traversal of matrix, right? That's the essential part. And actually there are also spiral traversal of a binary tree, right? So here let me see the key point, the idea. So the key point is, how do we detect places where the direction should be changed? So basically two things: how to detect position for direction change, right? This is the one. And the second and the related question is how to update direction. So once we know about or get a good understanding about these two points, the problem is very straightforward. First, let's look at the first question: how to detect position for directed change. So actually, once we hit a boundary, so for example here, then we need to change direction by rotating 90 degrees clockwise. So here the boundary means either the boundary of the matrix so at the very beginning, or the boundary that the matrix hasn't been set. For example, so this is a boundary here, and this is the boundary, and this is the boundary. So after we traversed 5, so here this guy is the boundary because this one is already set, right? So in other words, the boundary is the boundary for the inset blocks that the values haven't set yet. Or at the very beginning, it can be the boundary, which is the boundary of the original matrix, right? By n. So with that said, so let's look at how to update the direction. So here we're going to use the rotation matrix to do the update. So in this problem, actually the rotation matrix is 0, 1, and -1, 0. So for this problem, we're going to first share the code and then explain the rotation matrix. So once we shared the details about how to get the rotation matrix, so I would encourage you to try Leetcode 54 or Leetcode 59. So they can be solved using the similar idea here. So now let's look at the problem. So the code. First, I'm going to make some preparations. So for this, so from the statement to the problem, I'm going to initialize a matrix. So like this. So I will initially set them to be -1, right? Because if we do not need to reset the value, it should remain to be -1. So for here, I'm just times m for a dummy index in range m. Here we can do this because -1, so it's immutable, right? But list is mutable, so we use this list comprehension in the outer layer. So with that said, also we need to set the first position. So we're going to traverse, that is 0, 0. The original direction, I'll call it dr, dc, is to be the horizontal direction to the right, right? So row index does not change, but our index, the column index, will change by 1. So with that said, we are ready to do the traversal, the spiral traversal, right? So this is basically a while loop, while height. So what we are going to do is that we first set the matrix, the current position we are looking at, to be the height value. So once this done, basically we want to update the direction, right? After detecting the direction, and then we are going to do what? Do height lit next. So that's the point. Then we are going to return the matrix. So that's the overall structure. But here, let's see how to detect the condition for direction change and how to update the direction. So let me write here. So if we want to update the direction to be this r to r plus dr, and the c to c plus dc, right? So we want to check the update condition and do the update. So the update condition is like this. So if r plus dr is in range, so right, so it's not less than 0, or r plus dr is not greater or equal than m, or for c, so c plus dc is not less than 0, or c plus dc is not greater or equal than n. Or another case is that we already set the matrix values, because from the assumption of the problem, node value is greater or equal than 0, right? So then we can check matrix r plus dr, c plus dc. So how to check if this value is set or not? We examine it equals 1 or -1 or not. If it's not equals -1, it means it's already set, right? So once we have this situation, either hit a boundary or meet a number that is a position that is already set, we're going to update the direction. So dr dc to be updated by so let's see, dr dc to be negative dc and negative dr. So and then we're going to update the direction, the position r and c equals r plus dr, c plus dc. That's all about this solution. So here, I guess the one thing we want to explain is that dr dc reset to be dc negative dr. How can we get that? So here, the rotation matrix for this problem is this one, 0, 1, negative 1, 0. So assume that we have a direction is dr dc. Then if you do the matrix multiplication, you will get dc and negative dr. So that's the update rule. So we will explain in a short while. And then after we update the direction, and then we update the position, and then what we do is we update the height to the next, right? And finally we return the matrix. So that's the overall thought for this problem. Let's do a special case check now. It passes the example 1. Now let's do a generic case check. Yeah, it passes the generic case. So I guess for now that's the whole solution. So basically it's a spiral traversal of the matrix. So let's explain a little bit about the rotation matrix and how we get it, right? So let's look at some formula. So a rotation matrix basically is like this. So assume originally we are at position x and y, and then we counterclockwise rotate this vector by theta degree. Then we arrive at another point that is x tilde or y tilde. So we claim that in this situation, the rotation matrix is given by cosine theta, negative sin theta, and cosine theta. So the deviation is actually very easy, right? So x tilde equals, assume that the vector has the length rho, so it's rho cosine theta plus phi, right? And similarly, y tilde is rho times sine phi plus theta. Then we expand the cosine phi plus theta and sine phi plus theta. We're going to get this expression. But notice rho cosine phi and rho sine phi equals the original x and y respectively. So we can write it as x cosine theta minus y sin theta. Similar for y. So here rho sine phi is y. So we have y cosine theta. And rho cosine phi is x. So we have x sin theta. So for these two expressions about x tilde and y tilde, we can write them in a matrix form. That is x tilde, y tilde is this rotation matrix times xy. That's the R here. So in the current problem, we change the change the direction clockwise and each 90 degree, right? So that is theta equals negative 90. So you can compute cosine negative 90 and negative sine negative 90 and so on. So basically it's 0, 0 and 1, negative 1. So assume that we have a dr dc originally, you can think of as 0, 1. Then you use this rotation matrix times this dr dc. Basically you get dc and negative dr. That's the direction update rule. So you have originally you have dr and dc. Then after you change the direction, you change dr to be dc and dc to be negative dr. So that's the thought. Let's come back to the problem. So in here, so we have we computed this rotation matrix 0, 1, negative 1, 0. So this is the original direction dr dc. So we multiply them, you get dc negative dr. That's the direction update rule here, right? So you have dr dc equals dc and negative dr. So that's all about this. So basically the key for this problem I would say is the rotation direction update, right? So with that realized, it's nothing but a matrix spiral traversal problem. So again, finally, so if we have more numbers than m times n, so this method still works. The only thing we need to add is a counter to count how many numbers we have set. If it excludes m by n, we just need to break or stop. So with that said, I guess that's all about this problem. And the video running long. Let's end here. Thank you.